what happens if we think of a two-dimensional one? We still can do this. We still can do it in this straightforward way. But what happens if we want to find what the cobordism groups are for example, that one, that dimension, or even in a general case, that one? Well, that's no longer straightforward. So we need some more machinery to do that. And well, here I'm going to repeat a little bit from Patrick's lecture from the other day. So we're going to have Grassmann manifolds revisited. Well, here's the definition that Patrick explained the other day of Grassmann manifolds. The Grassmann manifold is the manifold consisting of all unoriented R-planes to the origin. We can also have oriented R-planes, only just that for that I will be using the notation. I think Patrick also uses like this, with with the delta. So that's it, that's the Grassmann manifold. And well, the interesting thing is that the Grassmann manifolds can induce some inclusions that are some that you have here on the slide. And why is that? Well, because any R-plane can be included in the but just as we included in the R of dimension R plus n, we can also include this into one more dimension. So that's what we are saying here, that the Grassmann manifold of R planes can be included in R dimension R plus n, but it can also be included in a very natural way in R plus n plus 1. And if we let that go to infinity, we have this here, which is just the EOR that we met the other day, and it's the classifying space. And it's also called the classifying space of principal L bundles. Now, Grassmann manifolds have two different canonical bundles that I'm going to denote by the gamma Rn and gamma perf Rn. We'll be using mostly the universal bundle, which is most important for the dome construction. But in recent years, the orthogonal complement has also led to very, very interesting research. So now we're going to see a little bit about pullback constructions. There on the top left, we have a pullback construction. It's just that you have a map from a manifold M into R, N plus R, and you can pull this, well, if you have a dependent bundle, you can pull it back to have a bundle over M. And, well, similarly, if you have any embedding of M into the Grassmann manifold, then you can have your universal bundle over the Grassmann manifold, and in a similar way as this, you can use this pullback construction to construct the normal manifold over M. And as we saw before, well, just before in the previous slide, we already had met this part of the inclusions of Grassmann manifolds, the natural inclusions induced by the inclusions of planes. And well, above each of these, I have written the corresponding canonical bundles or universal bundles. So here we have the universal bundle over Rn, and so on and so on. And here, when we reach the infinity, you can write it just like R infinity or just like gamma R, which is the bundle over EOR. But this is important because we are going to use it a lot. And well, using this, we can sort of put this map here and then we can find a map between M going all this way through up to this infinite Grassmann manifold, or just classifying space. And why is this important? Because, well, if we let this central part of the diagram out, what we are just writing is a very important pullback construction, and this is called the classifying map. Something that is already said about the classifying map that we have already here in the board, and it also introduces a new idea that is that of the VRFR structure. Well, this is very neatly explained in a book by Stone, Nelson Cobordism Theory. So I'm trying to just give a taste of the idea, and it's very important when you want to derive a general form of the Dom Cobordism theory. Well, what do we have here? Well, in the middle we have a diagram that commutes. So this diagram should commute, and this VRFR structure is just given, well, it's denoted because of the VR up here and the FR up here. So if I have a classifying map from M to the infinite Grassmannian, what I want to have is that this map lifts to this mu tilde here. And well, we consider that any two liftings are equivalent if they are homotopic. Here, down here, you have some more details. Well, we want to have some example of the VRFR structure because that sounds a little bit abstract. So consider, for example, if we consider, for example, unoriented cobordism, what would the VRFR structure look like? Quite simple. VR is just going to be R, and this map, the F sub R, is going to be the identity. So for unoriented cobordism, instead of saying VRFR structure, we can just say R identity. If we were to consider oriented cobordism, it would look very, very much, well, it would look fairly the same, but we should need to introduce here the FLR, and then this would no longer be the identity. We need again a map, but we only have two choices for the map, and we only have two choices of orientation. So this could be just the identity or sort of minus the identity. And then this would be again the classifying map, and this would be the lift. Well, these are two examples.
Does it ever factor through something that isn't a classifying field?
Sorry?
Does this VRFR structure ever factor through anything that isn't a classifying? Both of your examples of
yes. Well, you always get a classifying space. So, well, it's sort of cobordism theorem using this general VR structure, then just stop proving it for any sort of cobordism that you can imagine. So it's really well, it's a bit more complicated because it's more technical, but in the end it makes things more general and easier. So, well, now we have up here that I've no longer put a VR-FR structure, because just as we had for the inclusions of Grassmann manifolds into higher and higher and higher planes until we get to infinity, we can also do that with our subscript R for the VR structure. And you have it like this. Why is this? Well, in this first part, we already know. It's just like the same as in the previous slide. You have it here, and then you have it there again. But of course, we have already met the inclusions of the Grassmann manifolds in one dimension more, and we can also do this with the subscript here with the R. So we are going to be including R planes in R+1, which is perfectly possible, and then we get this map. And in the same way, we can also do it up there and define these maps. So what do we get in the end? That we can pull this to infinity, and in the end, we don't just need to be saying VR, FR structures. We can just worry about which B we're taking and which F. So in the end, you go to infinity. So as this sequence can always be defined, any VR, FR structure, as these examples, for example, well, they always define a BF